For more information, please visit our website at DarkCybernetics.com. This is DarkCybernetics, Data Structures, Graphs. Follow our free course documentation. In this video, we will discuss the concept of using the graph in data structures, how to write the graph notation, where we have the big G and we have the collection of vertices, what we would denote as V, and the edges. In this video, we will also discuss certain applications of using graphs in data structures. We will not go into adjacency lists and other features. Well, for right now, we can say that the vertice, or V, is the positive value of the number of vertices here. We can also say that the vertices are also the vertex, right? And these vertexes or vertices are really denoted as the destinations or the locations we need on the graph structuring. And for E, the edges, we can say that the edges E are the sets of edges connecting so these could be the roads, right? So there's a set of edges connecting the vertices. Alright, so we have a graph G, and we are getting a pairing of vertices and edges where we have a number of vertices which are both positive, and we can say that we go to n-1 for those. We have a set of edges connecting the vertices, and these are edges, the vertices in V. So we can have the vertices the vertices are the destinations, right? So in a graph, we want to know where we are headed, and we would generally set some type of path, and there is generally a path cost in certain graph structurings for visiting a location. The location could be the store, it could be a house, it could be a neighborhood, it could be a road map. And they would of course have to follow the edges to reach a destination. And these edges sometimes incur a path cost on weighted graphs, which we will get into later. We can say that the edges are the paths ways to the destination. I believe we'll run out of room here, and we will just abbreviate destination with a few letters here. So we've talked about the graph, and we have a number of vertices, which are vertexes, and there are a set of edges connecting the vertex in V, and the vertices are the destinations, like the store, and the edges are the pathways to the destinations, or the roads. So on this journey, where we talk about graphs, we also need to talk about certain terminology associated with graphs. And there are terms which are similar and have various notions and reasons for using them inside of a graph. There is a bit more formal definition for graphs, but we will not go into that right now. We can also say that there are two types of graphs we will use and talk about, and the way these graphs are traversed are a bit different based on the type of algorithm we choose to use for our program. We can have an undirected graph. Let's write that here. In an undirected graph, we have There's bidirectional movement. You can go back and forward, and you can visit a node and go back with each part of each vertex, also referred to as a node. And in a directed graph, the traveler or the algorithm of sorts will only move in a particular direction. Suppose you can think about that like a river. The river only goes downhill. And a bidirectional or undirected graph is, suppose we had, this may not be a good example, but let's just draw up some nodes here, some locations or vertices or destinations. And there are 5 destinations, and we'd have to connect those destinations. Like in the real world, suppose this was a graph or a city where we had A and B and C and D. Suppose D is in the middle, and E. Like in a real map, all the destinations may not be able to be traversed from one location to another. So we'd have to connect the roads, connecting the neighborhood of the road here. So let's say A went to D, and D went to E, and D only went to C and E. All right. And what else can we say about this graph? Let's label this. So these destinations are the vertex. Let's put vertex here. And this blue line will represent of course, the edge. People generally get confused when you say vertex and edge. The vertex or edge you may think corner, but it's not the corner, it's the road connecting the path. And let's draw a line here. This circle here is the vertex, and this blue line here is the edge. Alright, so let's continue. Let's talk more about the undirected graph. Alright, let's move this word directed over to the top. And let's just get rid of it entirely. Alright, we'll need that. And let's talk about how we write notation for a undirected graph. In an undirected graph, we have a vertex, and as we said before, the vertex was V. So we would need to write out each one of the vertices, or vertices. So there was an A, a B, and we separate each vertex with a comma. All right. This is something we generally cover in graph theory or in discrete mathematics, but it's really simple. We can cover it here. All right, and then we would need to have a pairing of all of the connections inside all the edges and all the ones reachable. So if we can visit A and D, and then we can visit A and B, right? And then we should be able to reach D and E, and D and C, and then there should be a B and a C. But we might run out of room here on this graph. And of course E and C can reach one another. So there would be one, A and B would be one, A and D would be a connection, a route, and then D and E, or which we can say is bidirectional. But we'll run out of space here. We're just going to draw a line right here. So on your notes, you would have to add it. All right, what else can we say about the graph here? We can ask a general question about a graph. Suppose we were in the center of the graph. We were on node D. We could ask the question, what are all the reachable nodes from D, or all the reachable destinations from D? Okay, let's write that in here. Okay, so we're at the node D. We would talk about all the reachable locations from D, and this is what our algorithm would be more. Well, we would use some kind of path cost or some kind of heuristic to search the algorithm. So based on the path cost. So if we were at D, if this was a weighted graph, since this is an undirected graph, we can go both directions. So we're at D, we can reach A, E, and C. So let's write this, say E, A, and C. Okay, from D. So we can reach 3 nodes from D. Alright, moving right along. Let's talk about a directed graph, or some of the terminology associated with the directed graph. In a directed graph, or there are other terminology we can use, we can talk about the level of connectivity inside of a directed graph. So I write the word directed graph here first before we go into any other topics. Alright, inside a directed graph we can have weak connections and strong connections, and the area, or if this was like sorting or some other activity we perform on the computer, the information or the pathway we choose may be one directional. It could be linear. It could move only in like a circular linked list. It could move around to A, and then A could move to B, then B could move to C, then C could go back around to A, like in the swapping algorithm, or some type of, or these could be node connections or hash map information. We would then talk. We could also talk about other extenuations of the structuring here. We could add, if it was something like a weighted graph, or if it had some kind of path cost. Let's put it here. It's supposed to be weighted directed graph, but we have limited space here. There will be a path cost for traveling on the graph. We also have a weighted undirected graph. Alright, let's draw some numbers here. Let's write some numbers for our weighted directed graph. Let's see. Let's suppose from A to C we had 5, and from B to C we had 7, and from A to B we had 8. We could also get a sum of the amount, well, the cost to traverse the graph, which was 8 plus 7 is 15. Oh no, it's not 15. 8 plus 7 is a number. And 8 plus 7 is, well, yeah. Anyway, we can talk about properties of graphs, properties of graph. Alright, these are probably not the right properties, but as we can talk about some of the characteristics of graphs, we can say that the digraph, or the directed graph, is right. The edges have adjacent or a direction. So a directed graph and an undirected graph the edges are bidirectional, or two-way. So we can go both forward and back on the array. Okay, so we can say that the vertex or the vertices on the graph and where we have U and V are adjacent here. We have some problems with this art tool today. We can say that vertex U and V are adjacent if U, comma V are in the set of the edges. Alright, simple concepts here. We can have bidirectional graphs or have direction. An undirected graph, edges are two-way, and vertices U and V are adjacent if U, comma V are in the set of the edges, E. Alright, so let's move on to another concept here. Let's talk about the connectivity of a graph. A graph can also be unconnected, and this is still a graph. It's not connected, and that's also a graph. Because we can also have a road from one city to another, and another city could only be reachable from a plane, right? We cannot travel the road, but there's still a city there, and this is the real world here. Let's draw a line here, and we can also have some type of graph where there was a directed graph, right, where you go certain directions, and where we had an additional area which was bidirectional. And this map, you can say, is strongly connected. Right, this happens sometimes too for if we're designing a computer system where we have to reach a certain node. It's only accessible through one node, but other information is being poured into it, which happens a lot, you know. And we can say that we also have weak connections. This is going to be weakly connected. I'm not sure. Weakly connected. Let's write this here. Weakly connected. And let's write an example of weakly connected network. Let's write the cannot be visited by a simple path. Alright. So weakly connected graphs cannot be visited by a simple path. Alright. And a strongly connected graph we can visit by multiple nodes or paths. Alright. And we also have a graph that's not connected. So we went over not being connected, we went over weakly connected, and strongly connected. Alright. Let's move on to something else. Let's see. Let's use black again. And you can say that a graph is complete if the edges from each vertex or vertices to each or in every other vertex Alright, so a graph is complete if the edges from each and every other vertex is, what is that right here? Well, so we can say if it's reachable from every other vertex. So we can have a self loop here. That's a self loop, right? Because a node can also visit itself. All right, we can go over that. And we can also have tree structurings from graphs where we have nodes and they only go one direction. Right. Very familiar term. We've seen this before, so we can just go, we can skim over this. And traversals are very important in graphs. This may be review for some, but we can also talk about some terminology used in graphs. We can talk about a walk. And a walk is a sequence of vertices and edges. So if we visit a certain a path, we take a path and we go through 1, 2, 5, 7, and that would be just a sequence of vertices we visit. We went on Highway 6 and got off at the grocery store. This would be like a walk. It's the path we've used. And so we can say that a walk is a sequence of vertices and edges in a graph, and we can repeat. And they can either be open or closed. Alright, simple enough. A walk is a sequence of vertices and edges in a graph, and these can be repeated. They are either open and closed. We can say that a graph is dense if the edges in the graph close to the if the edges in the graph are closest to the maximum number of edges. So we can say that the graph is dense if the edges are closest to the maximum number of edges. Right? We can say that a walk is a sequence of vertices and edges in a graph. We can repeat, and it can be either open or closed. We can say that the graph is sparse or sparing, right, if the edges are closest to the minimum number of edges, right? So that sounds, we know if it's dense, we're close to the maximum number of edges, and if it's sparse, it's closest to the minimum number of edges in the graph. Alright, so we have some terms here. We're doing a walk, dense, sparse. And so we have to go into some other terms and some other features of graphs. We can say that the sparseness is dense and the walk is a sequence of paths. We can also say that this is dense. It's too much. There's too many connections. That would be a nice way to think about that. it's too many. If it's dense, it's too many. If it's sparse, it's fairing. Too many edges. Alright. So let's move on to another concept. One question people generally have while we're going over graphs: well, you need to use graphs for search algorithms, and inside of search algorithms, there may be cycles, and a cycle is what we said. It's just a loop. There may be cycles in graphs. You may go into processing several times. You may need to go revisit a node. It may even be a game state where you use nodes at linked lists to traverse your graph, or where you put your data. There are also the loop in a graph containing a graph at least 3 vertices. We can say that it's a loop in a graph. It has to contain at least three vertices to be considered a loop. That's or a cycle. And I put up here at the top. This is for a single cycle, right? Has to contain at least 3 vertices to be considered a cycle. Alright. Well, I'll try to underline it here. Let's really try to underline this again. Alright. So let's go over what is a forest. There's some type of error here. A forest in an undirected graph and that's right. Okay, so we're using the undirected graph in a forest, and it is anything or any 2 vertices are connected. Let's say that a forest is in an undirected graph is any 2 vertices that are connected by at least right. So a cycle is a loop in a graph where a single cycle has contained at least 3 vertices, and a forest is an undirected graph and 2 vertices are connected at least or connected at most one path. Okay, that's right. Acyclic or acyclic. Alright, put that down here. Call these buzzwords, and it can be disjointed. It can be a disjointed union. A disjointed union of trees. Alright, so That's easy to understand. We have a forest and a cycle, where a cycle is a loop in a graph. A single cycle containing at least 3 vertices. In a forest, an undirected graph, it has any 2 vertices connected by at most 1 acyclic disjointed union of trees. Alright. Alright, so we can say that the walk is the same as, what is the walk the same as? A walk is the same as it's a sequence. So we can say the walk is, we can use the implication thing. It is a trail. And there's no repeating. There's no repeating on a trail. You take a walk somewhere, you just go there, one direction. And there are no, I'm not sure where this line is coming from, but it's on here. Okay, as a walk is a trail, there's no repeating edges. When we take a path somewhere, we go a particular direction, we should not go back. So let's draw a line here. And can't stop these anyway. Use for a graph. Use for graphs. All right. All right. So we can talk about the uses for graphs. We have some distractions there, but we'll just push on this time. Well, some uses for graphs. We can use them for 3-dimensional graphics. We can use them for search algorithms. And they can also be used for, we can think about breadth first search, depth first search, uniform call search. Many of the artificial intelligence courses use graph search algorithms. We can use them for minimax. We can use them for what is it, binary space partitioning. We can use it for simulations. We can use it for fluids. We can use graphs to represent lexicons, or the text to string parse trees. We can use it for, there are many uses, especially in computer graphics, where we can use it for fluids, and we can also use it for, what is another good use for? You can also use it for games. If you imagine a game state, so we're at a particular location. And we can use it for heap searches, for chess, and where we pass the states. We can use it for social medias. We can use it for web browsers. We can use it. We can use a graph for anything. We can also use a graph to represent nodes in the linked list. So it's good to have a few examples we can use. We talk about graphs, and they also can be used for routing problems for vehicles and other structurings and data structures. In this video series, we can also talk about the web browsers. And for more information, please visit our website at DarkCybernetics.com.